let us get started. So we have the last day we discussed where I showed MATLAB Simulink implementation of a DC motor, and we looked at different cases. We tried to uh,
Sir, your voice
we
is
tried
bit
to
closer.
understand the different behavior. Is it okay now? Hello.
Yes, sir, it's fine now.
Okay. So the last day we discussed about we saw how to simulate a DC machine in MATLAB Simulink. We understand various aspects of the simulation, and we tried to see what happens if we do several things like um, applying field voltage, then applying armature voltage, changing that, reducing that, ramping the armature voltage up, step down, step up, different things, and we discussed and we tried to understand the different things. So today what we'll be starting is we'll be going through a brief systems theory, which will and we will discuss the systems theory in with respect to the system that we have already discussed and understood well, that is a DC motor. So wherever we will be going through any part of any um, we'll be understanding any terminology, we'll be taking the example of a DC motor and trying to will be discussing uh, what is that particular thing, particular quantity in a DC motor, so that our understanding is more concrete. And thereafter we'll go towards uh, controller design, which will also have its implementation part in MATLAB Simulink thereafter, once we finish that. So let us get started. So first of all, it's a question that what we actually mean by a system. Is my slide changing? Can you see the next slide? Okay, yeah. So what is a
Sir, able
system?
to see.
A system. Sorry.
Able to see the slide, sir.
Okay. So what is a? You are able to see the slide, right? Second slide.
Yes, yes, correct.
Okay. So what is a system? System is mostly a physical thing, because we typically want to describe things which are physical, present in this physical world. So it's a physical process, it can be told it is a physical process, or it can be some device also, or it could be a combination. It could be a combination of what to say different components. So a system might be a process, say any process, any physical process like heating, cooling, all those things also can be described as a system. Or it could be a device, like our DC motor is a device overall. Or it could be a combination of components, just like may have some resistance, we can have some inductor, we can have some capacitance. If these are components, if we combine them, then it becomes a system. So a system is maybe a physical process, a device, or a combination of components, but it also has to do something. It so that has to accept some output, accept some input or inputs, and that will be processing that processing the input, and that will give the output, that will produce. The system will have to produce an output or outputs. There may be one input or multiple inputs, or there can be there may be one output or multiple outputs. So overall, if I want to represent that, using a block diagram, say this is a system. I don't know what is there. That is a black box to me as of now. That will accept one or multiple input, and that will give out some output, or it can be multiple outputs also. So this is what we mean by a system. And based on the number of inputs and based on the number of outputs, you might have already heard these things like single input. If our system has one single input and it has a single output only, then SISO, this type of systems are called as or named as SISO system, single input single output system. Similarly, if we have instead of if we have multiple inputs and multiple outputs, then often in systems theory, so that is termed as MIMO system, multiple input multiple output system. So let us now try to fit our DC motor as the system. What are the inputs? We have to give the field voltage, we have to give the armature voltage. Now what are the outputs? Overall, it is the speed that we want to measure, and we are interested with the speed. That is the final goal of running a DC motor. We finally want to run the motor at a particular speed, and whatever torque the load will demand, the motor is supposed to deliver that much amount of torque while running at the same speed. So overall, we can tell that it is the mechanical speed or rotational speed that is the output. So in this case, it turns out that there are two inputs, the field voltage and armature voltage, and we have one single output, that is the rotational speed of the motor. So it seems that it has two inputs and one output. So it's a MISO system, multiple input single output system in that sense. But mostly we'll see that while operating a motor, DC motor,
Sir, torque
you
is
will
not
keep
the
the field
output.
voltage, you will apply the field voltage, and unless your torque is not the output, torque is an intermediate variable in that sense, because finally we want the motor to run at a particular speed. At that speed, whatever torque the load will demand, the motor is supposed to deliver that. So if the motor is not able to deliver that torque, then motor speed will go down. That is, we will not be able to run the motor at that speed. So in that sense, speed, obviously torque can be considered as one of the outputs if we want so, but uh, in that sense current is also one output, because we can so we'll go through we'll understand what we mean by outputs. And actually you are right, if we want, you can also consider say current. And torque is not cannot should not be told as output, because torque is not something that we can very easily measure. Okay, so in that sense outputs are those which we can observe or measure. So torque in that sense may not be considered directly as one of the outputs, but because current is also something that we can observe or measure. So yeah, you can consider current also as one of the outputs, but majorly in a major sense, once we are running a motor, our purpose is to run it at a particular speed. So we are mostly worried about the speed. So that is why I have indicated that speed is the major output of our DC motor system. Now the next discussion that I was starting is, when you are operating a DC motor, unless we are going to operate the motor with field weakening, that is when we want the motor to rotate at higher speeds compared to its rated operating speed, then we would need to weaken the field. We would need to reduce the field voltage and thus reducing the field current. Unless that operation is normally known as field weakening control of a DC motor. Unless we are going to operate our DC motor in that zone, mostly in the other zones we will keep this armature voltage as a constant. So during operation we will not be changing this uh, one of the inputs, that is the field voltage, regularly. So in that situation our DC motor can be considered as a single input single output system only. Like, we are only changing the armature voltage and we are trying to maintain speed while delivering whatever required amount of torque. So if our our field voltage is kept constant during the operation, then our DC machine actually becomes a CISO system. And as we'll go through the discussions, it will become quite obvious that what are the why are we so much so CISO system, there is always always a advantage that only we are worried about only one output and only one input we can change. So the control of that system becomes obviously quite easy, quite simple compared to multiple input, multiple output systems. So it's quite uh, easy comparatively to model this type of systems, CISO systems, to design controllers for those systems. So most simple, uh, for wherever possible like to we would like to have only one single control input, and we'll be trying to get the output whatever we want. So yeah, the DC motor, if we are operating with field voltage as constant, then it has one single out input, that is the armature voltage, and one single output, that is the speed. So that is about what we mean by a system. It's in again I'm repeating, it's a physical process or device or combination of components that accepts one or multiple inputs, process it, and produce some output. That is overall what we mean by a system. Now let us go to the next step. What is mathematical model of a system? So system, we understand. Mathematical is a derived term from mathematics. So obviously there is going to be some mathematical equations involved in it. And model is what is a model? Model is a approximated version of a physical system. That is, if we approximate, if we do certain approximations and assumptions, then a physical system can be described by a model, and that model most often is mathematical. So what is a mathematical model? Mathematical model is, again, is a mathematical representation. Mathematical representation of what? Of a system. We understood what is a system. Why is it used? It is used to describe and sometimes predict also its behavior. So whose behavior? The system's behavior. What do you mean by behavior? Or describe means we want to describe, suppose uh, how our so if we so let us go to an example, then it will it will become very clear. So it's a method. So mathematical model is used to describe the system using, because it's mathematics, so we'll be using some equations, and the equations will be obviously based on some physical laws. So some laws of physics. So it will be based on that. So for electrical systems, we have the laws of physics as the energy. So the, what is that? The conservation of energy, that comes up as KVL, and we have the conservation of charges that comes up as KCL. So KVL, KCL, these are important physical laws which are used to describe the or mathematically model a system. So KVL, KCL, these are the physical laws which we'll be using mostly. And these equations will be relating certain things. So equations will be relating, what are the different things they will relate? Obviously, because it will accept certain inputs, so it will have to, the equations must have the inputs in it. It also needs to have the outputs. Then there is something called, we'll understand what is that, states states of a system. So again, it is more specific to when we talk about dynamic systems. We'll again understand it better, what we mean by system, what do we mean by states of a dynamic system. And again, we have certain parameters. So last class we briefly discussed on these. We will understand these one by one. So what are the inputs and outputs of a system? So what are inputs? Inputs is obviously something external that the user applies. So some signal, it could be some signal like gate pulses, that is also one input that you give to your power electronic converter, or you're applying some voltage, so that is also some input to that. So it could be some signal level input or some power level input, so that will call as some excitation. So some external signal or excitation which is applied to the system. Those are the
Sir,
inputs.
I am
So for
unable
DC
to
machine,
hear your voice.
am I audible? Hello, am I audible?
Yes,
Am
you're
I
audible.
audible? Okay. So DC machine, if we take the consideration of a DC machine, what are the inputs? We have the field voltage, that is a excitation, that is not a signal level input, that is some significant amount of voltage. So that is one of the inputs. And we can also have armature voltage, that is another input of a DC machine. So that is like the example of inputs for a DC machine. Now what are the outputs? What are the outputs? It is some quantity. Obviously, inputs and outputs both are quantities, and the quantities will have to be of interest to us. So we are interested in that. We are interested in looking at what is the how much is the at what speed the machine is rotating. So it is of interest to us. So it is some quantity of interest that is produced by the system. So it is not one of the inputs that will be produced after processing the inputs by the system. So it is a quantities, some quantity or quantities which are of our interest and which is produced or which are produced by the system, and we should be able to observe them. Otherwise, why will they be of interest to us if we cannot observe it directly? Just for an example, we know that we apply some voltage. We know from our studies of electromagnetic fields that there will be some flux in the flux flow in the machine, but can we observe it directly? Like, we can obviously we can estimate it, but we cannot directly observe it. So generally it is the flux linkages, those, because we are not able to observe them directly. So those are some internal variables of our system. They are mostly not the output of the system. So we'll be able to observe the outputs. We should be able to measure them with some measuring instruments. Like if we want to measure the current, we can use some ammeter or current sensor. If we want to measure the speed, then obviously we can use tachometer or some digital tachometer to measure the speed. And because that is a quantity of interest to us, then mostly we would also like to control that quantity. So what are the outputs? So outputs are quantities of interest which are produced by the system, what we can observe, we can measure, and we want to control them. So for a DC machine, for an example, for a DC motor more specifically, it is, as I have discussed, this is the speed. It is the speed that we want the motor to run at, and at that particular speed, based on the type of load that is connected to it, it may draw some torque. So if we are having a DC motor that is coupled to a load, and when it is rotating at some velocity or some angular speed, the load may demand some amount of torque. But torque is not something that we can directly measure or very easily measure. It is not very easy to measure torque. So mostly, but speed is easy to measure. So it will be, so whatever is the torque demand of the load, that will not consider directly. We will want the motor to rotate at that speed, and for that case, whatever power it takes, or in effect whatever torque it will demand, the motor is supposed to fulfill that amount of torque demand. So for DC motor, it's mostly the speed, but also because uh, that is an important variable that is required if we want to control the speed, or in some sense we have to determine, so that is a measure of torque also. So armature current, because we can observe it, you can measure it, and we typically want to control it also, while trying to control speed. So armature current can also be told as one of the outputs of the system. And if we are going for field weakening control, in that sense, the field current, because if we want to control the field current to precisely go to the uh, go to the field weakening mode of control, then will be measuring the field current also. So then field current can also be considered as one of the outputs. So that's about inputs and outputs of the system. Now any system, or more specifically, if we go for or if we look into dynamic systems. So what is the opposite form of dynamic? It is static. So static systems and dynamic systems, these are majorly two. In one way, if we want to uh, if we want to classify systems, then one type of system is a static system where the output, say y, some output that is a scaled version of input. That is where this k is a constant. So that means present input is sufficient, the information of present input is sufficient to decide, or is sufficient to describe what is going to be the output, what is going to be the present output of the system. So this type of systems is known as static systems. Example, suppose if we have a resistor system, so it's a resistance. And what is the input? Input is we apply some voltage. We apply some voltage, that is the input, and some current is flowing through it, and the current is actually the output. Current is actually the output of the system. So how are voltage and current related? If it is a DC case, DC voltage and DC current, then V equal to IR, so I equal to V by R. So written in another way, 1 by R into V. So 1 by R, the resistance can be the if the temperature, the variation of resistance with temperature is neglected, then the 1 by R coefficient, that is a constant. So our resistance is a typical case or example of a static system, where if we want to know what is the current flowing through a DC system, a DC system having only resistances, then we only need to know what is the present input, what is the present voltage that you have applied. If it is 10 volt, if it is 2 ohm, you can directly tell that yeah, it is 5 ampere of current. But dynamic systems, what do you mean by dynamic systems is the only the present input is not sufficient to describe the present output. That means we need some more information to describe a dynamic system. And in dynamic system, the minimum set of, it could be internal variables or some of the internal variables may be the outputs also. So minimum set of internal variables in general, I'll say that completely describe the present condition of the system. So it is the set of variables, the minimum set of variables. If you know the variables values at a particular given instant, if you know the next input, then you will be able to predict what is going to be the future output. That is the that set of variables is defined as the states, as the state. Because what do you mean by state? State is condition. So what is the condition of the system? If we know certain the values of certain variables, the internal variables, then you know what is the state of the system. In that state, if some input is given, you know what is going to be the output. So if you know the present state, if you know the present state and say future input, that information will be enough for you to tell what is going to be the future behavior of the system. Right? That is what we mean by states. Now let us have some example.
Sir, sir, future input we may not be know. Can't we say it as a past state and the present input to know the present behavior? Why
So
not this case?
no, yeah, I will take an example, then it will become clear. When we want to express the behavior means we always know what is the future. We'll understand once it is discussed, you will understand what do we mean by future in this sense. Future is not something uh, that is that we do not know in all cases. We do not know the future outputs, but future input in the next instant, what is going to the input, because we want to see the behavior of the system. Then we have to define the input. So that means input is always known to us. Any future input is known to us. It can be one step ahead or two steps ahead. What we want is always known to us. So suppose you want, so you are running a system of motors. So say for that you are doing some processing. For that your motor speed needs to be say 1000 rpm. So this is your motor speed profile. You have your process, say some industry, some steel industry or something. You are doing some processing with that, with your motor. Uh, so you know that for your operation or for your process, the motor speed needs to be, say it needs to ramp up first from 0 to 1000 rpm. At 1000 rpm it will have to rotate at say 1 minutes. It will rotate for 1 minute, and after that, for the successful production of your for successful completion of your process, you need to decelerate the motor, and then again as a ramp in some at some rate, and then you want to run it at you need to run at 500 rpm. Then again with ramp you need to decelerate the motor to the final speed. So this is something that is defined by your need. So you can say my need is going to be. So for that, you will have to define what is going to be my input, the input that I will be requiring to apply. So that means you need to know what is going to be the next input that I will apply, and only if you know the system well, then you will be able to apply such a input that will yield this type of final output. So what you are when you are running a control system, one thing, two things you are very clear: what you want, what is the final thing that you want, and what you are going to apply next. These two things you always know. How well you know the system, that that comes in the matter. So that decides how well you can change the input, so that finally you get what output you want. So future input is always known to us, because we know because we are the one who are going to apply it. So we know what next we are going to apply. So future input is not the problem, but future output, in order to predict it, we need the states of the system. So I'll take one example that will make it very clear. So let us take the case of a field voltage, the field voltage or the field circuit of a DC machine. So what is that? The differential equation is something like Vf is equal to Rfif plus Lf DIF dt. So I'm taking the simplest case, not the armature one, because it has another problematic thing called as back EMF. So let us not consider that. So if I make the differential term separate, then it will become 1 by LF Vf minus IFRF. Now in this system, I is so I'll erase a part of it. I don't know why. Okay, it seems due to some reason I'm not able to erase anyway. I'll continue. So this is a system. This is a system. Just bear with me. This is a system where we are applying some input. The output is IF, and we are modeling that system with this differential equation. So that is, this is the mathematical model of our system. And if we know our system well, or if so we'll understand what is the state of this system. So IF, what is IF? That is integration 1 by LF Vf minus IFRF into T. Say we take the variable as tau, and the tau, for knowing the value of I at a particular instant, say at a particular instant, say t, we need to know, say t1, we need to know the all the so we need to do integration. Tau is from minus infinity, tau is equal to from minus infinity to this instant, t1 instant. We need to do integration for all this. For all this duration, we need to do the integration, right? So can we reduce it further? Can we reduce the integration? So we can
Minus
always
infinity
write,
to 0.
tau equal to minus infinity to say any known instant, say t0, such that t0 is, so t0 lies in between infinity, that is eternity back during the time of creation, and t1 is the present instant, the instant with which we are interested in. So minus infinity t0 LF Vf minus IFRF t tau plus the same thing t0 to t1, again a1 by LF Vf minus IFRF into d tau. So this thing is nothing but the current, the field current at the instant t0. So if I go to the next slide, although I had yeah, this slide corresponds to something else, but still let me continue. So say this is the field current, and there are some inputs also. Say field voltage is something, so we're applying some field voltage for from eternity, and we are getting some field current also. So this is like minus infinity, this is say t0, and this is say t1. So the integration, the previous integration, whatever I wrote, that can be written as this term plus I at t0. So that means if we know the value of current at t0 instant, we need not know what are the past inputs, or what all things happened in past. We only need to know since this instant, what are the inputs, what kind of inputs are applied, and if we know that, we'll be able to predict what what kind of uh, output the system will produce. So only if at this instant, say t0, we know what is the field current, that is nothing but if t0, this value, and if we know after that After that, what are the voltage? So if I'll just write that equation once more for the benefit. So if we know this if at t0, and after that if we know from tau equal to t0 to t1 what all inputs are applied, right? What all inputs are applied, then always we will be able to calculate what are going to be the currents after that. So that means the state of this system is nothing but the output itself, that is the field current. The field current itself is the only state, that is the minimum variable, the one variable, a single variable only, whose value if we know at any instant, any future inputs if we know, we will be able to predict the future outputs also. By future I mean this is the present. If we know what happens, if we know what are the inputs after that, we'll be able to predict what are going to be the outputs after that. So it's a general thing. So if we have dynamic equations or differential equations, and we will have, if we remove the integration parts and we only describe the our system using differential equations, that means only we have some derivatives, the variables whose time differentiation will be done, those are the state variables of our system. So if I try to write down the equations of the field of the DC machine, like the first equation, the field equation is VF equal to IFRF plus LF DIF dt. Second equation is VA equal to IA RA plus LA TIA dt plus EB. Third equation is electromagnetic torque is equal to J d omega dt plus B omega plus load torque. Now there are certain other things also, like EB, that is some constant into IF into omega. The electromagnetic torque is some constant into field current into armature current. And if the load has some characteristics, speed torque characteristics, say it is a fan load, then the load torque can be considered, or if it is a fan load, then it is uh, proportional to square of speed. It could be proportional to speed also for some other kind of load. So this describes the entire DC machine system. Now you can see that you have three differential equations, and there are three quantities whose differentiation is time differentiation is being done. So what are they? They are field current, armature current, and speed. So these are the states of a DC machine, DC motor system. So this system has only three states: IF, IA, omega. So if we know the values of these three variables at any instant of time, and if we know what are the field voltages and armature voltages after that, we'll be able to tell what are the field currents, what are the armature currents, what are the speeds after that instant. So I hope the concept of state is well
Sir, could you
understood.
please repeat
Any
the
question?
last point, please? Hello.
What do you mean by the last point?
Like the states
From the
you have
differential
mentioned.
equations?
After
Sorry?
differential equations, we have three states. That is
Correct.
fine.
Yes.
After that, you have made one point. Could you please repeat that?
Okay. I made a point that suppose again like this thing only, we know that these are variables, so these are changing. So this is if, this is ia, this is the speed. If we know the values of these things at a instance at t equal to t0, we know these values, and we know what are the inputs after that, say how the vf changes, how the va changes after that t equal to t0 instant. We will be able to say what are going to be the behavior of these three variables if, ia, omega, and thereby we'll be able to say the torque, also will be able to say the back emf, everything will be able to say about the system after that. So that is the beauty about states of dynamic systems. If we know that, we know everything about the system, right? So now let us come to the this slide's contents. What are the parameters and variables of a system? So what are the parameters? So parameters are typically fixed quantities. Fixed quantities whose value does not change significantly during the operation of the system, and the quantities that describe the characteristics, that decide the characteristics of the system. I think someone is unmuted.
అవి ఉతికిన బట్టలు అయ్యి ఇప్పుడు నేను వచ్చేటప్పుడే వేసుకుని మంచి గుర్తు వాషింగ్ మిషన్ ఇది వాసన చూడండి.
Okay, so parameters are fixed quantities whose values do not change significantly during the operation of the system, and parameters are the ones that describe the characteristics of the system. So what do you mean by characteristics? We'll understand, like you can just consider that time constant is one of the describing factor, one of the factors, one of the characteristics of the system. So you understand that if we know the value of, so what are the parameters? Let us identify that. So the resistance of the field coil, we understood that it depends, yes, it depends on temperature, but the dependency is quite weak, so it could be considered as a constant. Again, the field winding inductance, we saw from our discussion of the field in the DC machine, we saw that the inductance can slightly change with rotor position, but that is quite weak in a DC machine. So why to complicate our life, let us consider it as a constant quantity only. Again, armature resistance, dependent on the temperature, so indirectly dependent on the current through it, but why to complicate our life, we'll neglect that small dependency and we'll consider it as a constant. Again, armature inductance, same story as field inductance, again a constant. J, the moment of inertia of the system, that is decided by the size of the shape, material of the rotating system. So it's the moment of inertia, polar moment of inertia of the rotating system, typically a constant. The frictional coefficient, if it is a frictional type of friction, that is where the frictional torque is proportional to speed, then the frictional coefficient uh, can be considered as a constant for a wide range of operation. Then again, this k is a constant that relates the back EMF to the field current and omega. Again, this k is the same k that relates the electromagnetic torque to the product of field current and armature current. And if it is a load, fan load, where or any type of load where the load torque and speed has certain relation, there will be some proportionality constant also. So this is also a constant. So overall, if I only talk about because this load is something that is not part of our DC motor, that is something that is connected to the motor. So we will not consider the load torque equation as part of our system, but other than that we have the field winding resistance, the field winding inductance, we have the armature winding resistance, armature winding inductance, we have the mechanical system J and mechanical system B, and we have the constant K that relates the electro that is related to the electromechanical energy conversion, that is speed to EMF or uh, current to torque. So these are the quantities whose values do not change significantly over time during the operation of the motor. So these are the parameters, or these are termed as the parameters of our DC motor system. Now what are variables? Variables can be anything whose value changes. Whose value change. So variables means it varies. So any quantity that can change. So it is a very broad term. It's a broad term used for, so under the variable it can be the input variables, the output variables, the state variables. So all these quantities whatever we have discussed earlier, all these are variables because the values of them can change significantly over during the operation. So in a nutshell, if we want to describe, or if we want to describe the mathematical model in a broad sense, how can we do that? So mathematical model is something that takes the input. So okay, it is not about the mathematical model, but it is the inter relation between these quantities, the input, state, parameters, and future state and output. So if we know the input, if we know the present state, if we know the input, if we know the parameter values, we'll be able to say what are the future states, what are the outputs. This is in broad term what are the so what is described by the differential equation or the mathematical model of the system. So if we
Sir,
know,
here
so
input is future input or present?
yeah, input is obviously future input. Present state means it takes care of all input from
Past to present.
eternally past to the present,
Okay.
and future, this is future input, and what are the future states and what is going to be the output, right? So if I again go back here, the present state considers the impact of the present input, and it need all the future input with the information of the parameters, it will be, you will be able to tell what are going to be the future states and future outputs. So just this equation, if you see this field current equation, if you know the present state, that is current at t equal to 0, if you know the parameters ILF and resistance, you will be able to, if you know the future inputs, that is VF, how it varies from how it is from T0 to T1, then you will be able to calculate how this future state will vary, right? So that is about the whole discussion. If we know present state of a dynamic system, if we know the future inputs, if we know the parameters, we will be able to come up with the future states and the outputs of the system. Now let us conclude our discussion by, or yeah, two more points for today. So let us discuss why mathematical models are needed, or what are the utilities of a mathematical model of a system. So why do we need, why do we need to model systems mathematically? Why? There has to be some uh, incentive towards doing that. Otherwise, why to do all this math and all these things? So first thing that allows us to analyze the behavior of the system. So suppose we have a system, say a DC motor. I want to see what will happen or how the motor will behave if I apply some voltage. If we say just the way we did last day, the motor is stand still, we suddenly apply some step in the field voltage. We need to see how the motor will behave, and after that, suppose I want to see, I apply some step in the armature voltage. I want to see how the motor will behave. So all these things, one way to uh, understand the behavior of the system is to run it physically. We'll be able to, will let us give some voltage, let us apply some voltage in armature field, let us measure the outputs. We'll be able to understand the behavior of the system. For this case, it is the DC motor. So the utility of a mathematical model is that if it is a reasonably accurate model, if we know the mathematical model, then we do not need the physical system to analyze its behavior. We can simply make a mathematical model of the DC motor. We can apply the same inputs that we want to apply, and we want to see, we can see what are the how is the behavior of the system, and analyze behavior that is very close to predict response. That is also, those are quite close. So predict response means if we apply something, now it is something is happening. If I do something in a different way, if I change the input voltage in a sense, how will the outputs change? That is like predicting the response. We need to do that for, so just like we saw that if we, with the field excited and the motor not rotating yet, if we suddenly apply a very large armature voltage, a very huge current will flow to the armature because there is no back EMF, and it will damage the motor. So because we had a mathematical model that is accurate enough, that describes the physics of the system, so we got to know that. So we will not apply the same kind of a thing input, we will not do the same kind of a thing in the while operating the actual motor of the system. That will ensure that our physical hardware motor that does not burn, or that there is no damage to that. So it's always good to analyze behavior or predict the response of the system with the mathematical model, rather than applying some going on applying some inputs in the physical system and observing its outputs. So the third utility is design controllers. Till now we have only understood the behavior or the prediction of response of the system. But if we want the output, that is the response of the system, in such a way, we will be able to come up with controllers with the knowledge of the mathematical model that will help us apply the kind of inputs that is required to meet the output requirement. So suppose whatever I discussed earlier, Suppose we want the motor speed to be like this, to follow some kind of profile like this, where this is speed. Now, if we know the model, mathematical model of the system, it will be able to, so we'll be able to come up with a profile of armature voltage that is required to meet this speed profile, not only in steady state but during the transients also, during this transient. So this time, if that is also very crucial, then we'll be able to the dynamic model, that the dynamic mathematical model of the system will enable us to design controllers that will help us, that will on its own, when given this kind of speed reference, it will generate voltage, or it will generate the voltage that is required to be applied across the motor terminals, that is required to get this type of speed profile. So designing controllers is crucial. Then obviously simulate systems, just like we did yesterday, the last class. We'll be able to simulate the system in a computer if we know the mathematical model of the system. And again, there is another point, the last point, that is to optimize the performance. Optimize means wherever there is the term called optimization, that means we can reach the output, or we can get the output, desired output, in more than one ways. So that means we can, because we have two inputs to our motor, say armature voltage and field voltage, and we want speed. Now there, because we have two inputs, it is possible that there will be multiple combinations of these two inputs that can take us to the same speed. Say VA1, VF1. If we apply this, then also the motor will rotate at omega 1, and if we apply VA2, VF2, then also the motor will rotate at omega 1. So optimization means there is a choice. We need to, there are options. We need to make a choice among the options. Then we'll go to the next matrix, like we'll calculate the losses, we'll calculate the efficiency, we'll try to apply from option 1 and option 2. If we know our model, we'll be able to calculate the currents for these inputs. We'll be able to calculate the losses, we'll be able to calculate the efficiency of the system if uh, if this input is given or this input is given. For both cases, motor speed is constant. That is not changing. But one case the efficiency may be say 90%, another case the efficiency may be 85%, because there are multiple losses happening and they are decided by the operating point. So obviously, so that means optimization. So first point that I made, whenever there is a term called optimization, that means we can reach the output, or we can meet the output with multiple input combinations. Now we have to analyze the possibilities with certain other terms. In general, that is the cost, or that is why during optimization, that is called the cost function, that we always try to reduce. So cost, in some sense, it is related to money. So efficiency, if your efficiency is higher, that means your electricity loss is lower. So if we if we if we have losses, and say possible input set 1, input set 2, input set 3, if we plot the losses corresponding to that, which is possible by with the mathematical model available to us, we can analyze the system and calculate the losses. Now with that analysis, we will be able to see that if we have say multiple points like this, we'll be able to identify the point with minimum losses, and then we can apply that point that will be able to that will be suitable for our system, so that it operates with minimum losses and maximum efficiency. So with the knowledge of the mathematical model, we'll be able to are able to optimize the performance of the system also. So these are the major utilities of having a mathematical model. Like, we'll be able to analyze the behavior, I have already discussed, predict response, design controllers, simulate systems, and optimize performance. So these are the major utilities of having a mathematical model of a system. Now this is the last point with which we'll close. So what are the forms of the mathematical model? Obviously, the first, we have already seen that is most fundamental, the differential equation model. Second, if we write down the differential equations in a different way, it becomes something called as state space model. Third, all these are continuous domain. These are continuous time domains. Next, difference equation model. This is something in discrete time, and this is very crucial in first simulation, computer simulation. So anything that you do in computer, things have to be discrete time. We cannot do continuous time things. We always have to digitize the time. We'll have to uh, we'll have to do some sampling and hold. So we will have to consider some sample. So we'll discuss it further. And obviously, if we want to do any microcontroller based digital control, then also this difference equations difference equation model will become important. If we do op-amp based control, then your differential equation form or state space model, or that, because that is continuous time or continuous time controllers, so that is fine. That those this analog controllers are continuous time controllers, so that is fine. But if we as soon as you want to implement some control in microcontrollers, that is digital control, so you need to finally implement your system, your controllers, in difference equation model, difference equation system. And for that you need to write the model, mathematical model, in difference equation form, not differential equation form. Now fourth is transfer function model. This is in frequency domain. Frequency domain means we are applying some signal with a constant, with a single frequency. What is a single frequency signal? A sinusoid. We are applying some input signal as sinusoid, and we are looking at the output sinusoid that is coming. So how this is input sinusoid, this is output sinusoid. A sinusoid has some amplitude, it has some phase. The output will also have some amplitude, it will have some phase with respect to the input signal. So how these two will be related, that is the transfer function. And this transfer function model, that is only so only one type of system uh, can be modeled, can be described by a transfer function model. The system has to be linear and time invariant. So only in short form LTI. Only LTI systems can be described LTI CISO system, single input, single output, because transfer function you only have one output and that one output is due to only one input. So LTI CISO systems can be described by transfer function model. So we'll understand these things more clearly. Linear, what is linearity, what is non-linearity, time invariant, time variant, CISO already you have discussed. So these are the four forms of mathematical models. Differential equation we have seen, state space model you might have studied, or it is nothing but the differential equation model only written in a different fashion, and there are different sets of different mathematical operations possible on that. So there is a separate topic called state space analysis of control systems or any system, state space modeling and control of physical systems. That is a separate model, a separate topic in itself. Difference equation, that is very specific to discrete time, that is important for simulation. Any computer based simulation, you need to you need to be able to convert your differential equations to difference equations. Now the fourth one is frequency domain, that is a transfer function model. So because it's only sinusoids, uh, so sinusoidal input, basic assumption is sinusoidal input will produce sinusoidal output. That means that is a linear system, and so only the sinusoids amplitude and phase will get modified. So only linear time invariant CISO systems are modeled, can be modeled as transfer functions, and that is actually a very um, well researched area. So transfer function model, if transfer function is known, then many things can be done. Many analysis become quite easy, intuitive. Designing of controllers is very easy. So there is always a push, even if we have a nonlinear system, even if we have a time invariant system, there is always a uh, desire to linearize that nonlinear system and design a linear controller for even nonlinear systems, because that is intuitive, that is quite well researched, and you will be able to see that transfer function, if we know transfer function, many things readily we can tell about the system. Okay, so let us close. Any question, any quick question?
Sir, I have a question from the previous classes. Um,
Okay.
we have in armature, because of the we have dynamically induced EMF, right?
Correct.
But in the stator field, while we are talking about the field circuit, because of the motion of the armature conductors, don't we get any induced EMF in the field? Like we are having back EMF in the armature, right?
Yes.
Can't we have similar kind of EMF in the field equation?
So I tried to discuss that while I was discussing the field circuit. So this is the field. This is the field. And if we have, so DC motor, we have cylindrical armature. And this is the other pole of the DC machine. This is our DC machine. Right. Now we have some winding. We have the winding on the stator. These are the two terminals of the field winding. Now suppose we are applying some constant current. Because of constant current, and there is a this is a magnetic uh, so this is a electromagnet with some small air gap. So obviously there will be some, I don't know why I'm not able to change color today, anyway. So there will be some flux lines that will get established in the core. So they will, half of that will flow this way, another half will flow this way. So they will cross the air gap and they will flow through the rotor like this. There will be a shaft also, so they will be divided in the two sides. Again they will cross the air gap and they will complete their path. Now you see that even if the rotor is rotating, because it's a cylindrical rotor, there is no change in the reluctance seen by the field winding, right? So the field winding inductance does not change with rotor rotation, right? Field winding inductance does not change with rotor rotation. That is a very clear. So for cylindrical rotors this is valid. So that means even if the rotor is rotating, there is no change of inductance of the field winding. Because of that, there will be no induced EMF in the field winding, even if the rotor is rotating. Now, but why is there of induced EMF in the armature winding? Because because we
because
have the
the
field.
coil is seeing the change in flux linkages.
Correct. Any single coil, because that is rotating, the coil, any one coil that is sitting there, that there is a change in the flux linkage of that coil with rotor rotation. But for field winding, there is no change of the flux linkage of the coil with rotor rotation, because there is no effective change of the inductance of the field winding, right? So that is why in field winding, even if the rotor rotates, there is no induced EMF. But for armature winding, because as the rotor rotates, the mutual inductance between the field winding and the armature winding, or more specifically the field winding and the armature coil, that changes, due to which the field flux that creates a mutual induced EMF in the armature coils, and due to the commutator and brush action, that quasi square wave induced EMF appears to be a constant DC quantity across the two terminals of the armature. Does it answer your question?
Yes, sir. Yes, yes.
Okay. Any other question?
So, for designing of the controller, why we need mathematical models? We can discuss in the next class, even if
Yeah,
possible.
when we'll design controllers, we'll see that we need the model. Otherwise, so overall, what is a what is a controller supposed to do? Suppose you have a system, a DC machine. You are applying a voltage. There is a speed. So a controller, what is the supposed uh, role of a controller? You will tell to the controller that I want this much speed. I want this speed. Controller will tell you apply this much voltage, and finally you will get, this is your physical system, this is your controller. This may be implemented analog, using analog electronics, or it can be implemented digitally, but it will tell you that apply this much voltage. And there is a small thing, controller itself will not apply the voltage, there will be something called actuators, or that is in this case a power electronic converter, that will be applying the actual voltage. Controller will only tell in signal sense that you need to apply this much amount of voltage, that's all. So the controller should be able to tell you, for getting this much speed you need to apply this much voltage. This information can only be obtained if you know the mathematical model of the system. Let us take an example of a resistance. A simple model, that is a resistance. You apply some input voltage, you have some output current. Now say it is a temperature, you want to maintain the temperature. This is coil where this is a temperature control system kind of a thing. So you know that if the coil current is this much, then what is the corresponding temperature, some degree Celsius, you know. Okay, so the relationship between temperature, say T, is equal to some constant into I. These are proportionally related. So you want some temperatures. For that, if you divide it by this constant K, you will be able to know what is the current you want. Only if you know what is the resistance of the coil, that is the model of the mathematical model of the system. So V equal to IR, so I equal to 1 by R into V. This is the parameter of the system. This is a static system. This is the one parameter. This parameter is a, if you know it, you know the model, you know the mathematical model of the system. If you know this 1 by R, or the R value, then controller will do this. Controller will so if you know I star, you know I star will be 1 by R into V star. So V star equal to R into I star. So it will have R as the gain, and that will produce that V star that you need to apply to the system, that you will apply to the physical system of a resistance, and that will have the output, that is current, and that will produce the temperature. So this is the controller, this is the plant, this is the physical system. This V by R, this is not, this system is nothing but a gain, that is 1 by R in all. So controller in this type of static system, it is, you can directly see that it is nothing but the reciprocal of the gain of the system. So this is 1 by R, that is R. So to decide what is going to be the gain of the controller, that is R, you need to know what is the gain of the system, so that you can take the reciprocal of that, and that is the controller gain of your system. As simple as that. So in order to decide the controller gain, you need to know what is the system gain, so that you can take the reciprocal of that.
Sir,
Is it clear?
but if in my system I have V such that it is less than V star,
Okay.
I cannot the maximum gain I can maximum V I can apply is only 1/9. Suppose 90% of V star is the maximum my real
Then you
system is able
cannot,
to
then you
give.
cannot reach. Then if your actuator, if your, suppose you have a resistance of 10 ohm, you want to apply, you want to pass 10 ampere through that. right? So you need to have a voltage source that is capable of giving 100 volt to it. If you have a voltage source that can only give 90 volt, no matter what controller you use, you cannot make 10 ampere flow through your resistance. Is it clear? Suppose you have a voltage source. You have a voltage source,
Yes, yes, understood,
DC
sir.
voltage
What you are
source.
saying is, in order to get in the desired performance in the closed loop, it must be possible with the open loop first, right?
Yes, yes. In the open loop, it should be possible. Otherwise, there is no way you can do that. Controller can
Yes, yes.
only improve the performance, improve how fast you can reach that final point. It should not be. It should not go into instability. Controller can ensure those things, but
Okay,
it must be possible through open loop. It must be possible to reach that operating point in open loop. Otherwise, controller can do nothing.
okay, sir. Okay, got it. Thank you.
Yeah. So just the example, if you want a
So,
resistance, if you have a resistance of 10 ohm, if you want to pass 10 ampere current through that, then the DC bus voltage, that the voltage source must be capable to give 100 volt. If it is higher, it's okay. If it is 150 volt, it's okay. You can change the if it is a variable voltage DC voltage source. So your controller will be tweaking that, the voltage, actual voltage. But if the maximum voltage is only 50 volt, no matter how much your controller changes, tweaks around the control input, it will not be able to pass 10 ampere current to that, right?
okay, sir. Okay, got it. Thank you.
Okay, thank you. Let us close then. Good night, everyone.